Good day, everyone. Welcome to lecture number 18 of Theory of Computation. And in this particular lecture, we are going to start a new topic related to theory of computation, and that is the grammars. So in this particular lecture, we will be discussing what are grammars and what are the different types of grammars and why grammars are important in studying this particular course. Okay, so up to lecture number 18, or we can say up to lecture number 17, we have discussed the concept about the formal language. Okay, so what is a formal language? We know any language is a set of strings. Okay, and in this language, we have discussed one particular type of language, and that is a regular language. Okay, and we know that regular languages are those languages which are recognized by a DFA or an NFA, or which can be represented using a regular expression. So this part we have already discussed. Okay, so we know a language is a set of strings. Okay, and for generating any language, for example, it may be an English language or any other language. Okay, for generating any language, there are some rules. Okay, so for generating any language, there are some rules, and those rules will specify whether a generated sentence is correct or not. Okay, or we can say for any language we have some rules, and based on those rules we can generate the sentences of that language. So here I am saying sentences. We can say we can generate the strings of that language, because in formal language the members of a language are the set of strings. So a mechanism to generate the sentences or strings of a language, so those mechanisms are based on some rules, and based on those rules we generate any language. Okay, so let me give an example. For example, we have a sentence. So let me write a sentence in English terminology. So let's say the sentence is, so let me write a sentence. The man ate the fruit. So let's take an example from an English sentence, and then we will generalize it to the formal language. So this is our sentence. Fine. So you can see that to generate this particular sentence, there are some rules in English language. Okay, so what are those rules? For example, if I have a sentence, so the rules are the sentence, some of the rules. I am not writing all the rules that are there in English language, but I am only discussing here some of the rules. For example, a sentence can have two parts. One is the noun phrase. So let me write it, noun phrase one, and another is verb phrase. Okay, for example, in this sentence, there are two parts. This is the noun phrase, and this is the verb phrase. Noun phrase and verb phrase. Okay. Internally, noun phrase can have two parts. One is the article, and another is noun itself. Okay, so I can write these rules. So sentence can be generated from a noun phrase concatenation with a verb phrase. Okay, and noun phrase itself, for example, noun phrase 1, it has an article concatenation with noun. So noun phrase is article concatenation with noun. So verb phrase can also have two parts. Verb phrase has the verb and the noun phrase. Let's say noun phrase 2. Fine. This article can be anything. For example, the and anything can be article. The article is that you have already discussed in your English language. So for example, here the article that is used is the. The noun that is used is man. Verb that is used is ate. So now we know noun phrase. Any noun phrase can be divided into two. One is article, another is noun. So this itself can be divided into article and noun. So let's say this is noun 1, this is noun 2. So this article again is the, and this noun is fruit. Okay. So using these rulers, I have generated this sentence. So what is the sentence? The man ate the fruit. Okay. So what were the rules here? So the rules were sentence can be generated using a noun phrase and verb phrase. Noun phrase internally can be article and noun. So let's say noun 1. Okay. Article gives us the, so that means article can be replaced with the. Noun 1 can be replaced with man. Verb, or we can say verb phrase. Verb phrase has two parts. One is verb and noun phrase 2. Verb is ate. So instead of verb, we can write ate. Noun phrase 2 itself has an article concatenation with noun 2. So article, we have already shown it here. Article is the. So noun 2 is fruit. Okay. So that means using these rules, these set of rules. So these are the rules. Okay. So using these rules, I have started from this S. So this is the start. So this was actually our sentence. So using this S, I have first used this rule, noun phrase, verb phrase. So sentence can be written as noun phrase, verb phrase. Then, so we have noun phrase, verb phrase. Now noun phrase can be written as, so you can see noun phrase 1 can be written as article and noun 1. And verb phrase can be written as verb and noun phrase 2. So let's say we are first writing for this side, left side. So this is left side. Let us first complete left side. So noun phrase 1 will be article and noun 1. So as I said, let's first complete the left side. So now which one is the left side? Article. Now article can be written as the. So article derives the. So is there any other left? No, we have completed. We reach to this member. So this member does not derive any other thing. Okay. So this is a one member. This is a member in this particular rules which does not derive any other member. Okay. Or we can say this is a member that is a part of final sentence, or we can say part of final string. So you can see this is the part of final string. What is our final string? The man ate the fruit. Okay. So now left side is completed. Again here, So we are first completing left side. This is completed, article is completed. Noun phrase one. Has we completed noun phrase one? No, because noun one is pending. Now noun one can be written as man. So is there anything that we can derive from man? No. This man belongs to this part. So this is also a member which does not derive any other member. So let's make a set of these. So these last ones which are part of the sentence. Let's make a set T. Okay. So this set T contains the, it also contains man. Let's see what else. Now we have completed left side. Now let's move to the right side. Verb phrase. Now verb phrase can be written as verb and noun phrase two. Verb and noun phrase two. So let's go this side first. Verb can be written as ate. Now can we derive anything else from ate? No. And you can see 8 is a member of this, or we can say 8 is a part of final string. So it also belongs to this set, T set. So what is this T set? T contains symbols which are part of final string. Okay. So now let's come to noun phrase. Noun phrase can be written as here, article and noun two. Article and noun two. Now, as I said, we will first complete the left side, article one. So this is left, noun two is right. So article can be written as the. So this the also belongs to T, but we have already written it here. Noun two is fruit. Okay. So this fruit also belongs to this T set. So at the end, from the left to right, so you can combine these. So what is the leftmost the? Then what is their man? Then what is their ate? Then what is their the? Then what is their fruit? Okay. So this is the final sentence that we generated using these rules. Okay. So using these rules, I have generated this. The man ate the fruit. And this particular graphical representation, or we can say deriving any string, any sentence using the rules, some specified rules, this is called a derivation tree for this particular string, or we can say for this particular sentence. Okay. And you can see that in the grammar there are two types of symbols. So one is this final symbol, which is the part of the sentence. Those symbols from which we cannot derive new symbols. Okay. From which we cannot derive new symbols. Those symbols are called terminal symbols. Terminal symbols. And they are represented by set T. Okay. T represents terminal symbols. And you can see that any string that we generate, it belongs to T star. Because these strings can only be generated from this T. And this T contains only these terminal symbols. Okay. And these particular symbols from which new symbols can be generated. For example, here article. From article we can generate T, the. Okay. And these symbols from which we can generate new symbols, and these are not the part of final sentence. Is there anyone from this part of final sentence? Verb phrase. Is verb phrase written anywhere here? Okay. So these symbols from which new symbols are generated, and which are not part of the final string. These symbols are called non-terminals. Okay, and they are represented by this set, N set, or we can say V set. We will mostly use V set because it is a standard that is used, but you can use N set as well. Okay. And what was this? This was a derivation tree for generating this particular string using these rules. Okay. Now let me write an example here. For example, S gives A, B, A. Okay. And here you can see that every string, or we can say every sentence, can be generated from this particular symbol, which is called a start symbol. Start symbol. Okay. So as I am saying, let's say this is an example. S gives A, B, A. B gives B. Okay. So now let's see how many strings I can generate using these rules. So S, or we can say B gives epsilon. This is another rule. Now S gives A, B, and A. So here you remember that A and B, these are terminal symbols, and non-terminal symbols are S and B. Okay, so always start from S. So now let's see which symbol we can rewrite. This cannot be rewritten. Why? This is a terminal symbol. This cannot be rewritten. Again, it is a terminal symbol. Now we can rewrite B. So now for B, there are choices. There are two choices. We can write for B, B. So if I write B, so it is complete. This is derivation tree. Derivation tree for which string? So which string it has generated? It has generated A, B, A. So this is a derivation tree for generating this particular string, or we can say this particular sentence. Now I can make another derivation tree as gives A, B, A. Now instead of B giving a small b, I will write epsilon. Then which string I will be generating? A dot epsilon dot A. That will be AA. So this is the derivation tree for this particular symbol. Okay. So we can see that any sentence, or I can say any string of a language can be generated using some rules. Okay. So what I am saying here, that any sentence or any string of a language can be generated using some rules. And in today's lecture, we will be discussing about a procedure for generating all strings of a language. And this procedure, or I can say these rules, okay, which are used for generating the strings of a language, these rules with some additional details is defined as a grammar for a language. Okay, so let me introduce you to the concept of grammar. Then we will repeat these things again and again, and we will see what is grammar. We will formally define what is grammar, and we will discuss different examples to see how we can generate all strings of a language using a grammar. So let me rub this and let me repeat this. Let me introduce you to the concept of grammar. So as I said, we have to discuss about a grammar. So basically, grammar is a mathematical model for generating sentences, or we can say strings of a language. So up to lecture number 17, we were basically discussing about the finite automatas. So what were the finite automatas? Finite automatas were used to recognize the strings of a regular language. Okay. So these were the mathematical models for recognizing the strings of a language, strings of a regular language. However, grammar is a mathematical model for generating strings of a language. So it is used for generating different strings of a language. And this mathematical model was first proposed by Noam Chomsky in 1959. Okay. The aim of this mathematical model was to parse natural languages. Natural languages. So parse means generating the sentences of the language that we are using. So Noam Chomsky's aim was to generate a mathematical model for a natural language such that I can use that mathematical model to generate all possible strings, or we can say all possible sentences for that particular language using that particular grammar. Okay, so as we have discussed here in our previous discussion, that in any grammar, so there are some rules, and using these rules, we derive a final string, or we can say a final string means a final sentence. Okay, so these are used to derive a final string, and using these rules, we always start from S symbol. S means start symbol. So this is the start for every string. So any string that can be generated from S symbol, that means that particular string can be generated using that particular grammar or using those particular rules. Okay, so any grammar has some rules, and those rules are used to derive a final string. And in these rules, every string starts with a start symbol. So when I want to generate a string, I have to start from this symbol, S symbol. This is called a start symbol. Fine. And apart from these symbols, there are two types of symbols. One type of symbol is called a terminal symbol. So these are called terminal symbols. And another type of symbols are called N symbols, which are called non-terminal symbols. Okay. So if I have a grammar, now, if I need to know what are the different strings that are generated using this grammar. So for this grammar, I should know following things. I should first know about these rules. Okay, rules that are used to derive a final string. So these rules are called production rules. Production rules. So I need to know the production rules. Okay. Second part that I need to know is the start symbol, S, which is called a start symbol. Then I need to know T. What is T? These are terminal symbols. And finally, I need to know N. What is N? or we can say instead of N, we can say V. Okay, we need to know V. What is V? V means non-terminal symbols. Okay. So can anyone say what is this S? This is a start symbol. Is this part of terminal or non-terminal? So S belongs to non-terminal because S is used to generate new symbols and it cannot be a part of final sentence, or we can say final string. Now the string generated by this grammar, it will belong to T star because T star means all possible strings that can be generated using terminal symbols, and we know string will only contain terminal symbols, so it will belong to T star. Fine. Okay, so this is the grammar. So let me introduce the grammar formally. So what is the grammar? So we can say a grammar grammar. So formally I can say a grammar is a four tuple entity. Tuple entity G is equal to V T S. So it has four parts. Every grammar has four parts. And what are those four parts? The first is V. V is the set of variables, or I can say these are non-terminals. Non-terminal symbols. Okay. And second is T. What is T? Set of terminal symbols. Okay. And third is S. S is a special non-terminal symbol, means it belongs to V. That is called a start symbol. Start symbol. Okay. And the fourth is P. What are P? P are the production rules. Okay. So these are the different parts of a grammar. So using these entities, using these different components of a grammar, we can derive strings from the grammar. Okay. So let's say I have some string S1. Now, if I want to say whether this string is generated by my grammar G. So how can I say whether this string is generated by grammar G? So I have to start from the start symbol S. Then I have to use production rules. And after using production rules, if I am able to generate S1, okay, so if I am able to generate this S1, then I can say this S1 is generated by this particular grammar. Okay, so that means if I have a grammar, and now if I have to see what are the possible strings that are generated from this grammar, so I have to always start from this symbol, start symbol, and then I can use production rules depending upon my choice in which manner I want to use production rules, and then finally I will generate some string. Let's suppose S1. Again, I will start from this symbol. Again, I will use production rules in different terminology, and I will generate another string. Again, I can start from start symbol and I will generate another symbol, another string S3. Likewise, from this start symbol, I can generate multiple strings. Okay, so using G, we can generate many strings. Okay. And the set of all strings, set of all strings generated by a grammar. Okay. Set of all strings generated by a grammar is called language of a grammar. Okay. Okay. So for example, here I am saying grammar is G, and these are the strings generated by this grammar. Then the language generated by this grammar, or we can say language of this grammar, will be the set of strings that are generated by this grammar. And for generating any string of a grammar, we have to always start from start symbol, S symbol. And how can we generate the strings of a language? Or we can say, how can we generate strings of a grammar? How can you generate the strings of a grammar? So you always start from start symbol. Okay. Start from this particular symbol, then use production rulers. And after using production rulers, we will reach to a final string. So this particular rulers that we are using, in which order, in whatever order we are using, this will be called a derivation tree for S1. Or in other words, this is also called parsing. Okay, so derivation tree of S1. Fine. So I have used production rulers to generate this S1, and this derivation tree will be, this particular tree will be called the derivation tree for this particular string. And this is how we can generate the strings of a grammar. Okay. Now let me give an example. As I was giving an example, a sentence is of, for example, if I can use the rulers. In our previous example, I was saying that sentence is made of two parts, noun phrase 1 and verb phrase. So basically sentence, the rule was sentence can be written as noun phrase 1 and verb phrase. So from this S, I used this production rule 1. And for this S, I have written noun phrase 1 and verb phrase. Then there were another rules. For example, verb phrase 1 was, it can be written as article and noun 1, and verb phrase can be written as verb dot noun phrase 1, noun phrase 2. Now here there are two schemes here. Either I can write verb phrase as, for example, verb dot noun phrase 2. So I will first complete right side. Then I will complete left side. Okay. Or in other words, I can first complete left side, then I will do the right side using these production rules. So we can say that for derivation tree, there are two possibilities. One is leftmost derivation tree, and another is rightmost derivation tree. So what I am saying, that using the grammar rules, we can reach to a final string either using leftmost derivation tree or using rightmost derivation tree. So what is leftmost? Leftmost means that first we are completing the derivation of leftmost symbol. Derivation of leftmost symbol. Okay. And rightmost derivation tree means that first we are completing the right, or we can say we are deriving the rightmost symbol. So either you can use first right side, then left side, or left side, then right side. Finally, you will get this string. Okay. So now, for example, if there is someone who has first done the left side, first completed left side, then did the right side. So that means he has used leftmost derivation. Let's suppose he has got string S1, okay, using some rules. Now, let's suppose there is another individual who is first completing right side using the same rulers that first one has used, and then completing left side. That means he is using the rightmost derivation tree. So that means he will also get some string S1. Will this string and this string be same? So what I am saying, that both individuals are using same rules, same set of rules. Okay. But one is using leftmost derivation scheme and another is using rightmost derivation scheme. Will they reach to the same string? Will the leftmost derivation based string and rightmost derivation string will be same? It is same in some cases and it is not same in some other cases. So we are going to discuss this when we will discuss the ambiguous and unambiguous grammars. Okay, so here we don't have to discuss this. We have to only understand what is leftmost derivation tree and what is rightmost derivation tree. Okay, so we can generate strings by deriving it, by making a derivation tree, and finally we will reach to a string. Okay, so let me give an example here. So let me write a grammar. So let's say G is a grammar. It has following V, T, S, P. Okay, let's say T terminal symbols are A, comma B. Okay, and non-terminal symbols are S, comma A, comma B. We know S is a start symbol, and production rules are following. So following are production rules. S gives A, S gives B, S gives AB, okay, A gives A, and B gives B. Okay. Now, if I am asking a question, what will be the language generated by this grammar? Okay, so what will be your solution? The solution will be language of this grammar will be the set of all strings generated by this grammar. Okay, set of all strings generated by this grammar. So let's see what are the different strings generated by this grammar. We know that we have to always start from the start symbol. Now see, S can be written as, so there are three choices. This is choice one. So this is production rule 1, production rule 2, production rule 3, production rule 4, and this is production rule 5. Now S can be written as, we can use production rule 1, production rule 2, or production rule 3. Let's say I have used production rule 1. So this is S can be written as A. Is there any other possibility of derivation? No. Why? Because we reach it to a terminal symbol. So one string is this, A. Okay. Let's say another string possible is, let's say here I am using production rule 2. So S can be written as B. So another string is B. Now another string S can be written as AB. This is another possibility. Now A can be written as A and B can be written as B. So what is the another string? S3 is equal to AB. So is there any other string that I can generate from S? No. I have to always start from this symbol. Okay, S symbol. Now, what are the strings that are generated? One is A, another is B, and another is AB. So this set forms the language generated by this particular grammar, this grammar that we are discussing. Okay, now let me give some more examples. Let me rub this and let me give some more examples, then we will move forward. Okay, so let me rub this first. So let me write another example here. So let's say G is a grammar. Okay. So again, it has 4 parts: V, T, S, P, where V is equal to, let's say, A and S, T is A comma B, and S is a start symbol, and production rules are following. The first production rule is S gives A, B, okay. A gives, if there is small a and capital A, terminal and non-terminal, it gives A, B, okay. And third is A gives epsilon. Okay. So what is the language generated by this grammar? Let's see what is the language generated by this grammar. Okay. So let's start from here, S symbol. So let's say I am using rule 1. So this is rule 1, this is rule 2, and this is rule 3. Okay. So using rule 1, I can derive A, B. Okay. So that means from S, I can write A, B. Okay. Now, so when we are deriving, we can either use a derivation tree or we can use this format. S derives A, B using rule 1. Now this derives, this one derives. So I can write for A, I can use rule 2. So for A, I can write A, B. Okay. Then this one derives. Now let's suppose A, B. I will write for A, this A. I can write epsilon. So it will be A, epsilon B. So it will be A, B. So is there any other possible? No. So I can see that from S, I have derived this string. In how many steps? In more than one step. So if I am writing S derives alpha, let's suppose alpha is something. So that means I am deriving alpha in how many steps? One step. If I am writing S derives alpha and I am writing here star, star means I am deriving alpha from S in more than one steps. So here I can directly write S derives this string A, B using more than one production rules. So this is one symbol, this is one string. Now let's suppose another string, another possibility is S derives A, B. Okay. In the first one, I was using, second time I was using rule 2. Now there is possibility I will use rule 3. For A, I can write epsilon. So that means AB. So the another possible string is AB, or I can write S derives in more than one step AB. Okay. Another possibility is S derives first AAB. Then this AAB, let's say I will use rule 2. So it will be AAB. Then, for example, let's say here I am using again rule 2. Okay, because rule 2 can be used again. AA can be written as AAAB. So I can write AAAB. Okay. This derives. Now here again, I can use rule 2 or rule 3. It is my choice because I can replace A or I can replace small a, capital A. Let's suppose I am writing epsilon. I am using rule 3rd. So it will be epsilon B. That means A. So this is another string that can be generated. Another string that can be generated is S gives AAB using rule 2. Again using rule 2. Okay, so here again I am using rule 2. Now I can use rule 2 again. So here I was using rule 1. Here I am using rule 2. Here I am using rule 2. Here again I am using rule 2. Now let's say I am using rule 3. So it will be A. So there are multiple infinite possible strings that can be generated using this grammar. Okay, and you can see that in all these strings that are generated by these particular rules, you can see all strings are of this type. First we have a more than one a or one a or one or more a's, and at the end we have only one b. Okay. So I can write language of this grammar is equal to a raised power n b such that n is greater than 0. So that means it will generate all strings of this type a raised power n b where n is greater than 0. So that means first n are greater than 0. That means it may be 1a or more than 1a's, and at the end we have b. So this will be the language generated by this grammar. Okay. So here I have given you an example where I am saying that if this is a grammar, can you say what is the language of this grammar? So we have shown it here how we can derive it. So we have to do some brainstorming, and then finally we will find out what is the language generated by this grammar. Now there may be an opposite thing. What is the opposite thing? For example, if you are given a language and you are said derive a grammar for that language. Okay, so there you should understand how we can derive a grammar for a language, but we will discuss that in detail when we are well acquainted with the concept of grammars. Then we will discuss those problems as well. But first let's only understand how we can derive the language from grammars. Okay, so let me give some examples here and you should derive the grammars for that. So or let's do one thing, let's wait for some time. Let's first complete the grammars introduction, then I will give you some homework where you are given the grammars and you have to derive the language for those grammars. Okay, so this up to this point we have completed the discussion. What is a grammar? A grammar is a mathematical model that is used to generate the strings of a language. And we have shown that a grammar has 4 parts. One is V. V is the set of terminals, non-terminals. T is a set of terminals. S is a start symbol, and P are the production rules. Okay, and we have also given an example, 1 or 2 examples, how we can generate strings from a grammar. Now let's see what are the different types of grammars in the formal automatic. What are the different grammars that we have to understand? Let me rub this and let's introduce the different types of grammars in theory of computation. Now we have to discuss different types of grammars. Okay. So what are the different types of grammars? So if we have a grammar, any grammar, so it can be classified based on the type of production rules. Okay. It can be classified on the basis of number of derivation trees. Derivation trees. And it can be classified based on the number of strings generated. Okay. So based on the type of productions or based on the type of production rules, the grammars are of following 4 types. Okay. So what are the different types? The first type is called type 0 grammar. Second type is type 1 grammar. Third type is type 2 grammar. And the fourth type is type 3 grammar. Okay. So on the basis of production rules, the grammars are divided in, or we can say the grammars are classified into following 4 categories. On the basis of number of derivation trees, the grammars are divided into following 2 types. One is called ambiguous grammar. Another is called non-ambiguous grammar. Okay. And on the basis of number of strings generated by a grammar, the grammars are divided into following 2 types. One is called recursive grammar. Okay. So recursive grammars generate infinite number of strings, and another is called non-recursive grammar. Non-recursive grammars generate finite number of strings. Okay. So these are the different classifications of grammars. Now, these 2 classifications, the classification based on number of derivation trees and the number of strings, we will discuss those types of grammars in our subsequent lectures. But in today's lecture, or we can say in this particular video, we will be discussing about the classification of grammars based on the type of production rules. And this classification is also called Chomsky hierarchy. Okay. So this classification. So on the basis of type of production rules, grammars are divided into following 4 categories: type 0, type 1, type 2, and type 3 grammars. So let's discuss these different types of grammars individually. So let's first discuss what is a type 0 grammar. Okay. So as I said, that this classification is based on the type of production rules. Okay. So every type of grammar has a different type of production rules. And what is the general structure of a production rule that determines what type of grammar it is. Okay. So type 0 grammar, which is also called an unrestricted grammar. Okay. Unrestricted grammar, or it is also called phrase structured grammar. And the language generated by this type of grammar is a recursively enumerable language. So we will discuss those languages. Recursively enumerable languages. Okay. So type 0 grammar, as I said, it is also called an unrestricted grammar or phrase structured grammar, and the language generated by an unrestricted grammar is called a recursively enumerable language. And for this type of language, we have a mathematical model to recognize this language, and that mathematical model is called Turing Machine. Okay. So we have to discuss Turing machines in great detail and about these recursively enumerable languages also. But here you have to understand that these type of languages are generated by a grammar which is called a type 0 grammar. Fine. So what type of production rules are in type 0 grammar? In type 0 grammar, the production rules are of this type. Alpha gives beta. Okay. Alpha gives beta. Where this alpha, this particular alpha belongs to V plus T star, V and V plus T star. Okay. So what does that mean? It means that alpha contains terminal and non-terminal symbols. So in the production rule, the left hand side may contain terminal and non-terminal symbols, but it must have at least one non-terminal symbol. So it must have one non-terminal symbol. So it can have 0 terminal symbols, but one non-terminal symbol should be there. That is why it is V plus T star, V and V plus T star. And this beta, it can be terminal or non-terminal, a string of terminal and non-terminal. For example, so here you can see this type of production rule is this production rule, alpha gives beta. Okay. So what is type 0 grammar or unrestricted grammar? So in the unrestricted grammar, production rules are of this type, alpha gives beta, such that alpha belongs to V plus T star, V and V plus T star. What does that mean? It means it contains terminals and non-terminals, but it must have at least one non-terminal symbol. And this beta, it belongs to V plus T star. That means it can be the beta may contain terminal and non-terminal symbols. Okay. So this is type 0 grammar. Now the second type of grammar is type 1 grammar. Okay. So type 1 grammar, which is also called, this type 1 grammar is also called context sensitive grammar. And the language generated by context sensitive grammar is called context sensitive language. Okay. And the automata that accepts, or we can say the mathematical model that recognizes context sensitive language is called linear bound automata. So what I am saying here, that type 1 grammar is also called context sensitive grammar, and the language generated by type 1 grammar is called a context sensitive language. And the automata, or we can say the mathematical model that accepts, that recognizes this kind of language, context sensitive language, is called linear bound automata. So the production rules in type 1 grammar, are same as there in type 0 with one restriction. Okay. And what is the restriction? The restriction is that the length of alpha, so the left hand side, of the production rule should be less than or equal to length of beta. Okay, so production rules are of this type. Alpha gives beta. Okay, it is same as type 0. Okay, but length of alpha should be less than or equal to length of beta. So we can say type 1 grammar is a subset of type 0 grammar. Or in other words, we can say context sensitive language is a subset of recursively enumerable languages. Okay, what I'm saying, context sensitive languages are subset of recursively enumerable languages. What does that mean? It means every context sensitive language is a recursively enumerable language as well, but the reverse is not true. What is the reverse? Recursively enumerable language is not every recursively enumerable language is not a context sensitive language. So what is the restriction here? That the length of this alpha should be less than or equal to length of beta. So that means when I am writing instead of alpha, I write beta. So that means the length of string will increase. Okay, it won't decrease. So as a result, this grammar is also called length increasing grammar. Why it is called a length increasing grammar? It is because when we are replacing the left side by the right side in our string, so the length of string will increase. Either it will remain same or it will increase. It will never decrease. Why it will never decrease? Because length of left hand side is always less than or equal to length of right hand side. So as a result, it is also called a length increasing grammar. So you can see that in type 1 grammar, there cannot be epsilon. Okay, so there cannot be, we cannot generate epsilon. Why we cannot generate epsilon? For example, epsilon can be generated if we have a production rule like this. S gives epsilon. So, but here the length of right hand side, that is S, is greater than the length of left hand side, because length of right hand side is 0 and the length of left hand side is 1. 1 is greater than 0. So this cannot be generated using type 1 grammar. However, if you want a type 1 grammar such that that grammar should generate epsilon as well, then you can have this exception. You can include this production rule, but you have to make sure that there is no production rule that has S on the right hand side. Okay, because for example, if there is some production rule like this, so by default it is a type 1 grammar, but since S gives epsilon, we can simply replace it with epsilon. That will invalidate our definition of type 1 grammar. So we can make this particular production rule a part of context sensitive grammar if you want to generate epsilon, but you have to make sure that there is no production rule that has this S symbol on the right hand side. Okay, so this is about the type 1 grammar. What is a type 1 grammar? So as I said, type 1 grammar is also called a context sensitive grammar. Okay, now the third type of grammar is type 2 grammar. Okay, so type 2 grammar is also called context free grammar. Okay, and the language generated by a context free grammar is called context free language. And the automata that recognizes the context-free language is called push down automata. Okay. So what is a type 2 grammar? Type 2 grammar is also called context-free grammar, and the language generated by a context-free grammar is called context-free language. And the mathematical model that recognizes the context-free language is called push-down automata. So type 2 grammar, it is like type 1 grammar. Type 1 grammar with one restriction. With one restriction. Okay. And what is the restriction? The restriction is that in type 2 grammar, so as we know that it will be like this. Okay. And length of alpha will be less than or equal to length of beta. And the restriction is, what is the restriction? The restriction is that this alpha can be only one non-terminal. So this is the restriction. For example, A gives BS. So this type of production rule, it is type 0 as well as type 1 and type 2. So because in type 2 we are saying this left hand side should be only a single non-terminal. Fine. So the same case is with type 2 as well. So type 2, for example, type 2, as I said, it is type 1 grammar. So that means it will also have this restriction. Length of alpha should be less than or equal to length of beta. So in type 2 grammar, if you want to generate epsilon, you have to again keep in mind that I cannot generate epsilon. However, if you want to generate epsilon, you can include this production as well. But you have to again make sure that this S does not appear on the right hand side of any production rule. Okay. So this is about the type 2 grammar. Fine. Now remains the last one, and the last one is type 3 grammar. So let me now explain type 3. So type 3 grammar is also called regular grammar. Okay. And the language generated by this particular grammar is called regular language. And we have already discussed that the mathematical model that recognizes regular language is called finite automata. So we have already discussed about a regular language. So what is a regular language? A regular language is a language for which there exists a finite automata, or we can say for which there exists a regular expression. And now there is another method. We can say a language is regular if there exists a regular grammar for that particular language. Okay. So this type of grammar, it is like a type 2 grammar, with a restriction, with one more restriction. See, at the higher level, we were having type 0. Type 0 has no restriction. Then type 1. Type 1 was type 0 with one restriction. Type 2 is type 1 with with another restriction. Type 3 is type 2 with one more restriction. Okay. So this is the most restricted grammar. Restricted grammar. And you can see that it is the subset of type 2 grammar. Okay. So type 1 is subset of type 0. type 2 is subset of type 1 and type 3 is subset of type 2. And the restriction in type 3 grammar is, so it is like type 2. Type 2 means that the productions are of this form. Okay. Length of alpha is less than or equal to length of beta. And this alpha is only a non-terminal symbol. It can only be a non-terminal symbol, a single non-terminal symbol. Okay. And the restriction is for this beta. This beta, it can be V dot terminal. So that means first one is non-terminal and second symbol is terminal. Or it can be the first one is terminal, second one is non-terminal. So for example, the production can be of this format. So here, first one is terminal, second one is non-terminal, or it can be of this format. First one is non-terminal, second one is terminal. Okay. And this one, this type of grammar is called left regular. Okay, please remember, beta can be V dot T or it can be simply T. T means it can be S give us A. Likewise, beta can be T dot V or simply T. And this type of regular grammar is called right regular. We can easily convert left regular into right regular and right regular into left regular. Okay, fine. So this is about type 3 grammar. So before concluding this, there are some more points about the type 3 grammar. So let me write it here. So in type 3 grammar, as I said, the production rules are of this type, where alpha is a non-terminal and beta can be this or this. If it is kind of this, then it is called left regular. And if the beta is, so when I am writing this \T, so it means these are two production rules. One is beta gives this and another production rule is beta gives this. So this type of grammar is called right regular. Now we have also extended regular or extended left regular or right regular. So let's take extended left regular. It will be beta gives V and then there can be more terminal symbols, only terminal. And in extended left right, it can be beta is terminals at the beginning, some terminals and then non-terminals. For example, beta can be VAAA, let's say, or beta can be AAAV. So this is kind of extended left regular and right regular. Okay. So this completes our discussion about different types of grammar. So we can say, if we write it, let's say, for example, this includes type 0 grammar, or we can say recursively enumerable languages. Fine. And the subset of type 0 is this one, which is type 1, or we can say context sensitive languages. Then the subset of type 1 is this one, which is type 0. Oh, sorry, type 2, which is also called, which generates context free language. Okay. And the subset of this is type 3, which generates regular language. And the subset of regular languages is another, which is finite language. All finite languages are regular. Finite language means a language which contains finite number of strings. Okay, so this Chomsky, we can say hierarchy includes, at the top we have type 0 language, or we can say type 0 grammars, then we have type 1, then we have type 2, then we have type 3. And for type 3 we have finite automatas, okay. For type 2 we have push down automatas. For type 1 we have linear LBA, linear bound automata. And for type 0 we have Turing machines. So you can see which machine is strongest. Turing machine is strongest, then comes the linear bound automata, then push down automata, then finite automata. So the push down automata has higher power than the finite automata. LBA has higher power than this push down automata, which is also called PDA. This is also called a linear bound automata. Okay, and Turing machines have the highest power among all these mathematical models. So this completes our introduction about the grammars and also the discussion about the different types of grammars based on the type of regular languages. Okay, so you have to keep in mind that this particular grammar, type 3, we have already discussed the language of type 3, that is the regular language. We have already discussed these languages, and we have already discussed the mathematical model that recognizes these languages, that is finite automata. So we won't be discussing about type 3 languages. Then comes type 1, type 2. So what is type 2? Type 2 is context-free grammar. And the language generated is context-free language. And the mathematical model that recognizes the context-free language is called push-down automata. Okay, so this is one topic. Other is type 1. We won't be discussing about type 1 because that is context-sensitive language. That is out of scope of this particular lecture series. But we will be discussing about type 0. Type 0 generates, or type 0 is also called unrestricted grammar. And the language generated are called recursively enumerable languages. And the mathematical model that recognizes recursively enumerable languages is called Turing machines. Okay, that is the second topic. So first, we will discuss the context-free languages, context-free grammars, context-free languages, and push-down automata. After completing this, we will move to another topic, that is type 0 grammars. So we will discuss about the unrestricted grammar, recursively enumerable languages, and Turing machines, and many other concepts related to the Turing machines. So from our next lecture, we will start discussion about the type 2 grammars, that is context-free grammars. So let's meet in the next lecture where we will be discussing about the context-free grammars and context-free languages. Till then, thank you everyone for joining this lecture.